Hello everyone, welcome to the week 6 problem solving session for pattern recognition and application course. I am Tanuka Bhattacharjee from IISc Bangalore. I am a PhD student over there in electrical engineering department. So in today's problem solving session, we will discuss one method of dimensionality reduction, which is the principal component analysis. We will solve some problems and discuss some concepts about dimensionality reduction principal component analysis method. So the first problem or the first question that we have is dimensionality reduction aims at two objectives are given. We have to say which is the objective of dimensionality reduction. The first option is project feature vector to a lower dimension, and the second is features in the projected space are orthogonal or uncorrelated. So before I answer the question, if anyone wants to volunteer to answer, what will be the correct option for this? Okay, I'll explain the idea. So one answer I got is option you are saying option 1, which is project feature vector to a lower dimension. Yes, of course that is correct, but not only that, dimensionality reduction is primary idea is you have to reduce the dimension to make it computationally feasible and so on. And for that you are trying to project the feature vector to a lower dimension. That is the primary idea, but along with that you also try to make the features uncorrelated in the projected space, or to make the features orthogonal in the projected space, because you do not want to have the same information in 2 or 3 or multiple features, because that is just redundant information. So you just want to have all unique informations in all the feature dimensions. So you want to make the features orthogonal, so that there is the correlation is not there. So whatever information is present in feature 1, that has no dependence with what is present in feature 2. So there is no redundant information, and you just want to get rid of all the redundant informations, and for that reason you try to make the features orthogonal in the projected space. So both of the options that are given here are actually aims of dimensionality reduction. You not only try to project it to a lower dimension, you project to such a dimension that in that space, in that projected space, your features will be uncorrelated, so that you do not have any redundant information. All your features give some new information in that projected space. So both 1 and 2 are correct for this particular question. Let us move on to the next one. Next one is, which of the following is or are true for PCA? First is maintains the separability of two classes, and second is projection direction is best in terms of minimum squared error. Again, if anyone wants to volunteer before I explain it. Okay, so the idea of PCA is it does not make use of any class information. So, it does not know about the two classes and there is no question of maintaining the separability of the two classes. It just tries to find the best representation of the feature vectors in terms of the minimum squared error. Just a minute. Yeah. So here the first option is not correct. It has nothing to do with the separability of the two classes because we do not even use that information in PCA. So, but the second option, that is projection direction, is best in terms of minimum squared error. That is the correct answer for this. So, this is only 2. So, you try to find such a direction along which your projected feature vectors are the best representations in terms of the minimum squared error. There is the minimum squared squared error between your projected feature vector and the original one is minimum if we project in this particular direction. But there is no guarantee that if you have two or multiple classes, whether those will be separable in that particular projected space or not. There is no guarantee in PCA. The guarantee is only that the squared error between your projection and original feature vector is the minimum. So, it is the best representation that you can get in that particular lower dimension. But what happens to the separability in terms of classes, that is not guaranteed because that information is not even used in PCA. Okay. If anyone has any question, you can put it in the chat. I will move on to the next question. So, the question is, when PCA is used to project data to 1D space, let us say the original feature dimension be any d dimensional feature vector and you want to project it to 1D space using the PCA algorithm, then what is the direction of projection? So, the direction of projection in this case will be the eigenvector of covariance matrix corresponding to the largest eigenvalue, because you are projecting to a 1D space. That direction will give you the best representation. So, that will give you the minimum squared error. As you have already learnt the derivation from the course lecture, you will already know that the answer is eigenvector of covariance matrix corresponding to the largest eigenvalue. That will be the direction of projection when you are using PCA to project data from some high dimensional space to 1D space. Now, if that is the case, the next question tells that show that while projecting feature vectors to 1D space, PCA selects that projection direction along which the projected data has maximum variance. So, you are trying to project feature vectors to 1D space, you have to use PCA and you have to prove that the projection direction along which the projected data has maximum variance, that particular direction is chosen by PCA. So, let us try to prove this. So, we will prove it in the reverse order. So, we will try to derive the direction along which the variance of the projected data will be maximum, and we will try to see if that is the direction that gets selected when you use PCA. We will use that approach. So, let us say that the feature vectors that we have or the data points that we have are given by x1, x2 like that till xn. So, we have n number of data points, small n number of data points given by x1, x2, xn, or in general xi, where I varies from 1 to n. And let us say these are some d dimensional feature vectors, you are trying to project it to 1D space using you are trying to project it to 1D space. Now you are trying to find that projection direction along which if you project this data, it will have maximum variance. So let us say that direction is the direction along which projected data has maximum variance be E. So let E be the projection direction along which if you project your data, you will get maximum variance of the projected data. So if you consider all possible projection directions, this will give you the maximum variance. So since this is the direction, we are just concerned about the direction, we will consider that E is a unit vector. So norm of E is 1. So your projected data, when you project the data along this projection direction E, the projected data becomes y1 will be E transpose x1. So this is just the orthogonal projection of x1 on the vector E. That will give you the projection of x1 along that direction, which is we are denoting by y1. So for any general xi, you will get yi, which is given by E transpose xi, where I equals to 1 to n. These are the projected the projected data in the 1D space are given by yi. The expression is E transpose xi. Now you want to see the variance of this particular projected data. You want to see the variance of these yi. So how do you compute the variance of yi? So the formula for variance, let us say V will be 1 by n summation yi minus mu tilde whole square I equals to 1 to n. So this is the general formula for variance, where u tilde I am denoting as the mean of the projected data. So u tilde is basically expectation of yi, or if you write in terms of sample mean, it is 1 by n summation I equals to 1 to n yi. That is the mean of the projected data is given by u tilde. So your variance is yi minus u tilde whole square summed over all I, and you are scaling by a factor 1 by n. So now let us try to further simplify this expression. So your V is, as you saw, 1 by n summation I equals to 1 to n yi minus tilde square. So first let us see what is mu tilde. So mu tilde is 1 by n summation I equals to 1 to n yi, right. This is equals to 1 by n summation I 1 to n, yi is E transpose xi. Okay. So here E transpose is independent of I, so we can take that out and we can put it as E transpose into 1 by n summation I equals to 1 to n xi. So the term within this bracket, this is basically the mean of xi. Let us say we denote that mean by mu. So your mu tilde becomes E transpose mu. It is basically the projection of your original data along this projection direction E is your projected mean, the data mean of your projected data U tilde, mu tilde. So if we put that here, yi is E transpose xi minus mu tilde is E transpose mu, that whole square. So this E transpose xi minus E transpose mu, this is basically a scalar quantity. You are taking a square of that. So you can also write that as, like, if x is x square, you can write that as x transpose x, and since here these are scalar quantity, so you can write it as square as the term within the bracket transpose that particular term, or it is same as this term into this term transpose. Since this is a scalar quantity, that does not matter. So you can write this as E transpose, I am taking common, so xi minus mu into xi minus mu transpose E. So I am writing, basically I am writing x square as x into x transpose. This is because x is a scalar quantity, that is why we can write this as this. So we are writing E transpose x minus mu into x minus mu transpose E. This is equivalent to the square quantity. Now is this E transpose and E, oh sorry, I somehow made a mistake here, so I will change it. This should be 1 by n, not 1 by 2. This should be 1 by n. Now since E transpose and E are not dependent on I, so we can take those out of the summation, and we can rewrite the summation as E transpose 1 by n summation I equals to 1 to n xi minus mu into xi minus mu transpose into E. Okay. Now if you look at it carefully, the term within the bracket, that is the summation term along with the scaling factor 1 by n, this is basically the covariance of the original data xi. That is the expression 1 by n summation I equal to 1 to n xi minus mu into xi minus mu transpose. That is basically the covariance matrix of the original data points xi. So if I denote that as sigma, then this variance becomes E transpose sigma E. So this is the variance of the projected data along the projection direction E. Now you want to select such an E so that this variance is maximized. So you want to maximize this particular quantity E transpose sigma E. You want to maximize that. So let us form a objective function for this maximization. Then if we form an objective function, then we can simply take the derivative of that objective function, equate that to 0 and find the required projection direction. We have to take the derivative with respect to E. So here you want to maximize this variance, or you want to minimize the negative of this variance. So we can write the objective function as j of E, that is equal to minus of E transpose sigma E. You are trying to minimize negative of E transpose sigma E. Now not only this, along with this you have the constraint that your E is a unit vector. So it is unit norm. So your constraint is norm of E square should be equal to 1, or E transpose E should be equal to 1. Right? So you add that constraint using a Lagrange multiplier lambda, So, this becomes your final objective function, minus E transpose sigma E plus lambda times E transpose E minus 1. Now, it is simple, you will have to select that particular E which minimizes this quantity. So, you will have to take the derivative of J E with respect to E and equate that to 0. So, if you take the derivative, so your J E is minus E transpose sigma E plus lambda times E transpose E minus 1. So, del J del E will be minus 2 sigma E plus 2 lambda E. This way you will equate to 0, or in other words you have sigma E equal to lambda E. So, as you know, this is basically the eigenvalue problem. So, here E is basically the eigenvector of the covariance matrix sigma and lambda is the corresponding eigenvalue. So, you found that if you want to maximize the variance of the projected data, you will have to select such a direction of projection which is basically the some eigenvector of the covariance matrix of the data. But there can be multiple eigenvectors, which one you will choose? For that, so you have the variance is equal to E transpose sigma E and you want to maximize this. So, from this equation, if you take your variance V is E transpose sigma E. Now from this equation, you have sigma E should be equals to lambda E. If you put that, you get E transpose lambda E. That will be your variance if you project along the eigenvectors. Now, you can take lambda to the left and E transpose E, and you already know that E is a unit vector. So, E transpose E would be equal to 1. So, this will be equal to lambda into 1. So, lambda. E transpose E will be, this term will be equal to 1. So, your entire term will be lambda. So, if you project along certain eigenvector E, the variance that you will get of the projected data, that will be equal to the corresponding eigenvalue lambda. So, since you want to maximize this variance, if you choose lambda as the highest eigenvalue of the covariance matrix, then and you project along E as the corresponding eigenvector, the eigenvector corresponding to the highest eigenvalue of the covariance matrix sigma, then you will get the variance V as the highest lambda value. So, your variance will be maximized. Because your variance is given by the eigenvalue, the maximum value possible is the highest possible eigenvalue. So, if you take the eigenvector E corresponding to the highest eigenvalue lambda, then if you take that as the projection direction, you will get the maximum variance of the projected data. Now, as you have already studied PCA, this is basically the direction that PCA selects to project the data. So, basically PCA selects such a direction so that your projected data will have maximum variance. When you project the data along the selected direction, which is basically the eigenvector corresponding to the largest eigenvalue of the covariance matrix, when you project along that particular direction, the variance of your projected data will be the maximum. So, basically PCA also tries to maximize the variance of the projected data, or it tries to project the data in such a space in which the variance is maximum. So, I derived it for 1D space. You can do it for any dimensional space which is lower than the than the original feature dimension. So, you will take the eigenvectors corresponding to the top k eigenvalues, let us say. So, you will project to a k dimensional space. You will take the top k eigenvalues and the eigenvectors corresponding to those eigenvalues. So, they will anyway be orthogonal. So, you will be able to maximize the variance in that k dimensional space. So, this was, by this we show that PCA projects the data in such a direction that along that direction the projected data will have maximum variance. Okay. I hope it is clear to everyone. If anyone has any question, you can put it up in the chat. I will wait a minute for you if you have any doubts. So, let us move on to the next problem. The next problem is given as, which of the following could be the direction of projection using PCA if the data points lie on the locus of the curve shown in figure. So, the figure shows you the locus of the curve on which your original data points lie, and now you will have to say that if you use PCA, what will be the direction of your projection? Is it x axis, y axis, or direction making an angle 45 degree with x axis in anticlockwise direction, or the direction making an angle of 135 degree with x axis in anticlockwise direction? So, anyone wants to answer this? I got the answer from Shima Shinde as C, the direction making an angle of 45 degree with x axis in the anticlockwise direction. Yes, that is the correct answer. So, I'll explain it for the others. So, as you saw, you basically in PCA, you are projecting along the eigenvector corresponding to the largest eigenvalue of your covariance matrix. So, this is basically the direction along which if you project the data, you will get maximum variance of the data. So, you can think of it as you will get the maximum variance of the projected data along this direction. So, basically your data set has the maximum spread along this direction. So, for example, if you project all this data, samples that you have on this locus on, let us say, the x axis. Let us say you are projecting all the data orthogonal projections on the x axis. Your spread will be somewhere from here to here. In this region all your data will be projected. Again, if you project it on the x2 or y axis, all your data will be projected in this spread. So, this is basically kind of a estimate measure of your variance. So, these two will be, if you project along y axis, that variance is even less than you project in project along x axis. You can visually see that. Like that, if you take this particular direction, then your projection will lie in this range. So, the spread will be maximum along, or the variance will be maximum along this particular direction. So, this is basically the direction of the eigenvector corresponding to the largest eigenvalue of the covariance matrix. So, this is basically the direction along which if you project the data, the variance of the projected data will be maximum, or your data set has the maximum spread along this particular direction. This is the direction along which PCA projects the data. So, the correct answer is option C. So, this is basically the line. This line is basically the one making a 45-degree angle with x axis in the anticlockwise direction. So, this is the correct answer for this, because this is the direction along which your data has maximum spread. So, this is the direction along which if you project the data, your data will have maximum variance, projected data will have maximum variance. So, this is the direction chosen by PCA. Okay. Now, let us work out a complete PCA example. So, here the problem is find the projection of the following vectors onto 1D space using PCA. So, you have been given 8 samples, 8 data points, each of which are 2D. So, you are originally your data points in the 2D space. You will have to project it to 1D space using PCA. So, if, as you know, the direction along which you should project in PCA is the direction of the eigenvector corresponding to the largest eigenvalue of the covariance matrix of the data. So, first step in this PCA example will be to compute the covariance matrix of this particular data set. So, you know the general expression for covariance matrix. So, if I write that as sigma, sigma is the covariance matrix. This is basically 1 by n summation I equals to 1 to n xi minus mu into xi minus mu transpose, where n is your total number of data points, xi from i1 to n are the actual data points x1, x2, and mu is the mean of the data points. Then you have the covariance matrix is given by 1 by n summation I equal to 1 to n xi minus mu into xi minus mu transpose. So, to compute this for this particular data set, first you will have to compute mu, the mean of the data set. So, first let us compute mu. So, mu will be 1/8 of the summation of all the feature vectors. So, that will be 24 20. 24 20. So, this will be equals to 3 2.5. So, the mean vector mu is given as 3 2.5. This is the mean vector. Now, you will have to compute xi minus mu for all xi. So, you will just have to subtract mu or the mean from each of the data points or each of xi. So, let us just write down the xi minus mu vectors. Those will be, first you have 1 1, you have to subtract 3 2.5 from that. So, you will get minus 2 minus 1.5. Next one you have is 3 0. You subtract mu, you get 3 minus 3 0, 0 minus 2.5 is minus 2.5. Then you have 3 2. You subtract mu, you get 0 minus 0.5. Then you have 5 1. So, you get 2 minus 1.5. Then you have 1 4. So, you get minus 2 1.5. Then 3 3, that will give you 0 and 0.5. Then 3, 5, that will again give you 0 and 2.5. And the last example is 5, 4. So this will give you 2, 1.5. So these are basically your xi minus mu points. I have a comment as 0 from Shima. Can you tell me what you mean by this comment? I didn't get your point. Have I made any error in the computation? Zero and minus 0.5. Okay, you are talking about the third example, I assume, right? 0 and minus 0.5. Yeah, so this is from 3, 2. So you originally your example was 3, 2, your data point was 3, 2. You are subtracting the mean from that, which is 3 and 2.5. So you are just doing this subtraction. So you get 0 and minus 0.5. Is it clear to you? You simply okay, can you just unmute and tell your doubt?
Hello.
Yeah.
Ma'am, I am not getting how this becomes 0 and minus 0.5.
So your this is, you are talking about the third example, right? X3.
Third.
So the original value was 3, 2, and this was your original data point, right?
Okay.
This was 3, 2, and you are computing x
Yes.
minus mu. So the mu you got is 3, 2.5. So simply have to subtract this mu vector from your x3. So 3, 2, from that you minus 3, 2.5. So 3 minus 3 will give you the first coordinate as 0, and 2 minus 2.5, the second coordinate, you will get as minus 0.5.
Okay, ma'am. Thank you.
Okay. So like that we have got all the xi minus mu points. So these are the 8 values. Okay. Now we will have to compute the sigma. For that we need xi minus mu into xi minus mu transpose for all xi. So let us first try to compute that. The first example you have is your x1 minus mu is minus 2 minus 1.5, minus 2 minus 1.5, this into this transpose. So you will get the product matrix as 4, 3, 3, 4, 3, 3, 2.5. This is for your x1. This is basically x1 minus mu into x1 minus mu transpose. Now similarly we will do for x2, which is 0 minus 2.5, 0 minus 2.5 and the transpose of that. So you will get 0, 0, again 0, and 2.5 into 2.5 we will get 6.25. Now the next one is 0 minus 0.5, 0 minus 0.5, 0 minus 0.5, 0, 0, 0, this will be 0.25. Yeah. Moving on to the fourth data point, 2 minus 1.5. 2 minus 1.5, and the transpose of that we get 4, 3, minus 3, 4 minus 3 minus 3, and this is 2.25, right. So you get 4 minus 3 minus 3, 2.25. Now let us take the fifth example, minus 2, 1.5. Minus 2, 1.5 into minus 2, 1.5 transpose. So this is again 4 minus 3 minus 3, 2.25. Then we have 0.5. Then the next example is 0, 2.5. I will put it here, 0, 2.5 and 0, 2.5 transpose. So you will get 0, 0, 0, 6.25. And the last data point you have is 2, 1.5. 2, 1.5. 2, 1.5 transpose. You multiply, you get 4, 3, 3, 2.25. Okay. Now, thus you got these terms, xi minus mu into xi minus mu transpose for all I. So, to get the sigma matrix, what you will have to do is sum up all these matrices that you got and divide that by n. N is your number of data points, which is 8 in this case. So, you will have to sum all those matrices up and divide all the elements by 8. So, you will get sigma as 1 by 8. The matrix will be 4, 16, 16, 0, 0, 22. Okay, and so your final will be 2, 0, 0. This is 2.75. So this is your covariance matrix of the data points that you have. Covariance matrix of all the x values is given by this particular matrix, 2, 0, 0, 2.75. Now you will have to find the projection direction. So as we have told multiple times, the projection direction is basically, if you are trying to project to 1D space, it is the eigenvector corresponding to the largest eigenvalue of the covariance matrix. So, you will to find the projection direction, you will have to find the eigenvector corresponding to the largest eigenvalue of this sigma. So, since sigma is a diagonal matrix, you can readily say that the eigenvalues lambda 1, you will have 2 eigenvalues because it is a 2 cross 2 matrix with rank 2, and the eigenvalues will be the diagonal elements because this is a diagonal matrix. So, you will have 2 eigenvalues, 2 and 2.75. So, the larger one among them is 2.75. So, you will have to compute the eigenvector corresponding to this particular eigenvalue 2.75. That will give you the projection direction according to PCA. So, let us compute that. So, to find eigenvector, your equation will be, let us say E be that particular eigenvector, sigma E should be equals to lambda 2 E. Okay. Your sigma is 2.75. Let's say I put the two dimensions of E as E1, E2. Your lambda 2, you will have to put the largest eigenvalue. So, that will be 2.75 into, again I will put E as E1, E2. So, this is your equation. If you solve this equation, you get the eigenvector corresponding to your largest eigenvalue. So, you will have two equations from this. First one will be 2E1 equals to 2.75 E1. Next will be 2.75 E2 equals to 2.75 E2. So, from the first equation 2E1 equals to 2.75 E1, you get that E1 should be equals to 0, right. So, the first equation gives you that E1 will be equals to 0, and the second equation, this one 2.75 E1 E2 equals to 2.75 E2, this says that all values of E2 will satisfy this equation, but since we are concerned with unit vectors, so we will put E2 equals to 1. So, your final E, the eigenvector corresponding to your largest eigenvalue of sigma, is given by 0, 1. So, this is basically the direction of projection for PCA. Okay. So, you got the direction of projection. Now, the original question was to find the projections of the original feature vectors. So, to get the projections of the original feature vectors, so you want to get the yi's, which are basically E transpose xi minus mu for I equals to 1 to n. These are basically your projected data points, right. As you have already derived in the class for PCA, your projected data will be E transpose xi minus mu. So, xi minus mu you have already computed for all the data points. So, here you have the xi minus mu for all the data points. So, you simply have to take the inner product of E with this xi minus mu points to get the final projected data, and your E is 0, 1. So, the inner products that you will get will be minus 1.5 for the first data, which was minus 2 minus 1.5. So, you simply do the multiplication 0, 1 transpose minus 2 minus 1.5. So, you will get minus 1.5. So, basically if you take the inner product of 0, 1 with your data points, then you will basically get the result as the second dimension of your feature vectors, the xi minus mu vectors. If you will get the second dimension of these vectors as your inner product answer. So, for the first data point, the projected data will be minus 1.5. For the second, it will be minus 2.5, then minus 0.5. I will write it down, minus 2.5, then minus 0.5. Then you have minus 1.5, 1.5, 0.5, 2.5 and 1.5, 0.5, 2.5, 1.5. So, these are basically the projected data along the direction of projection according to PCA. So, this is basically the complete procedure to project your original 2D data in our case, or in general some d-dimensional data to a 1D space using the method of PCA. Now, let us quickly look at the last problem that we have. Find the projection of 2,7 onto 1D space using PCA. Projection of this on 1D space using PCA with the principal component obtained in problem 5. This should be problem 6 by the way. Sorry for that, problem 6. So, the projection, the principal component, this is basically the principal component. This direction is basically the principal component. So, the principal component obtained here is 0, 1. So, your principal component E is 0, 1. You have to take the projection of 2,7 onto 1D space using PCA. So, as you saw, the formula for projection will be E transpose x minus mu. E is basically 0, 1, x is your 2,7 and mu you have already computed in the previous problem as 3, 2.5. So, mu is, as you computed before, it is 3, 2.5. So, if you simply take this 0, 1 into x is 2,7 minus mu is 3, 2.5, that is 0, 1 into minus 1, sorry, 4.5, right. And if you take this inner product, you will get 4.5. So, this is the projection of 2,7 onto 1D space using the PCA method with the principal component obtained in our previous problem and also mu obtained in our previous problem. So, the projection we got for 2,7 is 4.5. Okay. So, that is all I have planned for today. If you have any questions or doubts, you can raise it now. Okay, so I do not see any questions in the chat box, so I assume this is fine to everyone. Okay, so let's meet in the next week with the next set of problems. In the next week, we will basically see one more type of dimensionality reduction, which is MDA. We will solve some problems on that. So let's meet in the next week. Thank you guys for joining.